Uh, so, uh, Hello everyone. Welcome to this problem solving session. We will start now. This week we will be covering about the uh, impedance matching and for the active network, which earlier. Earlier we were dealing with. Earlier it was the we discussed the impedance matching for passive network. So this time we will discuss the impedance matching for active net passive network, for example, your your match load. So passive network which only contain equivalent models of R, C, and L, and which does not have any active power source. So only those network we consider the impedance matching. And this week content was mainly primarily for impedance matching for active network. That we will discuss today. What are the criteria for matching? Also, I will be briefly summarize the content which was discussed in the main lecture. So if you want to have very detailed understanding of that, so please go through the reference cited and please go through the lecture materials once again. I will be briefly give an overview of the content presented in this week. So basically, our first and foremost concept is basically different types of Smith chart. So basically, in Smith chart is a kind of polar plot between real part of reflection coefficient, normalized reflection coefficient, versus a real part of so this is a real sorry so this is a real part of reflection coefficient, and this is uh, the imaginary part of the reflection coefficient. So this is on this axis imaginary part of lamp. This is the plot in this, and basically it is the mapping from Z plane or impedance. If you plot impedance in the 2D plane, so real part of uh, Z to imaginary part of Z to the coordinates like axis are the reflection coefficient. Basically, the relationship from Z to reflection coefficient that drives your your Smith chart. So if we plot the Smith chart, so basically the this center point is gamma equals to uh, gamma equals to 0, or where the reflection coefficient is 0, and this other periphery correspond to gamma equals to 1 case, and basically and that other circle you can draw is this is the uh, unit resistance circuit, and this is the unit conductance circle. So basically, you can draw the Smith chart in this two axis. Basically, this you can draw the impedance uh, Smith chart, and admittance Smith chart, and also impedance admittance Smith chart, where you level both the axes. So this correspond to normalized impedance equals to 1 case. So the normalized impedance, this circle correspond to normalized impedance equals to 1 case, and this impedance correspond to the normalized impedance. So y equals to 1 case, and so yeah, so this is y equals to 1 and this is z equals to 1. So also there are a reactive element. Basically, so you can draw the reactive circle. So basically, these circle, if you draw these plot, so these are the okay. So that basically you can draw the reactive part. So basically, along this this also you can draw like this. You can draw the this resistance circle. You can draw like this. So yeah, so on this if you move on the Smith chart along this curvature of which black and dark, basically there the resistance is constant, and if you move along this gray line, so where there the susceptance or like the reactance is constant. So this so the positive part correspond to the positive susceptance, and the axis below correspond to the negative susceptance. So that in the positive part it will behave like an inductor, and in the bottom part it will behave like the capacitor. So in uh, the typical case. So yeah, sorry, I just lost my network. Oh, I'm sorry, I lost the connection. So now it's back. So let's just uh, get to point where we were. So basically, like if you move around this circle, so basically these are the constant resistance circle. So these are the constant resistance circle, and basically a similar equivalent you can draw in the same same plot. If you draw the admittance, if you plot the admittance, so basically that basically these are the positive admittance. So let me draw it. So these are the positive admittance, and this is the negative admittance. Similarly, you can draw the this positive in admittance, and this is the so so this is the the circle corresponding to susceptant, and this is the positive value and negative value. And this circle, if you draw if this circle you draw, so this circle is basically these circle if you draw, then basically those are the susceptance, those are the admittance circle. So these are the admittance circle, and this the black circle here correspond to the unity admittance. So basically uh, so now if you so now let's just see, suppose you have a load impedance. So if you have a load impedance, and let's say so this so let's say you have a load impedance. So basically let's say you have a load impedance of let's say 0.5 plus minus j times 1.0. So let's say this is the negative uh, capacitance, and then let's say you are adding a series inductance to this load. Then what will happen? So if you draw the Smith chart, so basically you draw the 1.0 susceptant and zero point 0.5 admittance, zero point 0.5 zero point 0.5 resistance circle. Then basically you can draw this load point at the Smith chart. So let's just draw that point. So let's just take a impedance Smith chart. So this is your unity reflectance circuit, and then basically if you want to draw, so basically it's the point so this is the zero, so real part is zero. So real part of zl is equals to 0, and this is here the uh, so just so here the real part of zl equals to 1. Here the real part of z equals to 1, and in between it will be a in between it will be a zero point 0.5 value will come in between. So that we can draw with this circle. So we can draw with this circle. This is 0.5 uh, 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 zero point 0.5 uh, resistance circle, and basically then basically we can just draw the susceptant. So correspondingly, we can find the value of susceptant because this is minus 10, so it will be here only. So the this is your ZL point. So now what will happen basically if you add a series inductance? So basically this will move around the constant resistance circle. So basically that you will move around this constant resistance circle, and that basically you can so no, this is the uh, yeah, yeah, I think this is correct. So that basically you can move around this constant resistance circle. So then if you add the susceptance in series, inductance in series, then that will move clockwise in the constant resistance circle. So basically this point will transform to this point. So this point will get if you add a positive susceptance, positive inductance in the series, then this point will move to here. So that basically like the this, and if you add the impedance inductance in the shunt, basically it will move in the negative direction. So this if you add the resistance in the shunt, basically it will move opposite in the constant resistance circle. Similar effect is for the capacitance. Basically, if you add the series capacitance, then it will move. So let's just write. So series inductance. So that will move clockwise in the direction clockwise on the constant resistance circle. And if you shunt resistance, if you add shunt inductance, that will move anti-clockwise in the constant resistance circle. Similarly, if you add series capacitance, then basically it will move uh, the clockwise. So it will move clockwise in the on the constant admittance circle, and a shunt capacitance anti-clockwise on the constant admittance circle. So that is like if you add a reactive component, basically that will happen. So so the main idea so for active circuit actually this impedance matching from both load side and source side is necessary. Otherwise there won't be any like the power transfer will not be maximized, and you will have you will have few consequences because of that imperfect power transfer. So what will happen, let's say I'll draw a let's say this is a transistor amplifier. So let's say you connected a impedance matching network. So there are two impedance matching network. One is source side, other is load side. So this load side is connected this, So and basically this. So if you see like here, the reflection will be reflection at source side. Here the reflection will be reflection at load side. So why this like the impedance matching is necessary? Because like one problem, like the consequence of imperfect impedance matching, of imperfect impedance matching. So basically, this will cause the like the efficiency. So first is the efficiency, and other thing is basically the reflected power. Basically, if it is reflected back to active devices, it may cause it may uh, cause the instability. So basically, because this is the analog, so if you add the like typical reactive and those component, it may your amplifier will become the unstable. So there may be some nonlinearity will occur, or like the either the output will get very much amplified, or very like very highly attenuated or very highly amplified, and that will lead to instability condition, and that like some saturation will happen within the component of the amplifier. So these in these conditions actually like your impedance matching is absolutely necessary for active networks. So basically like to so the this designing this impedance matching network is very crucial, and basically that so basically you can use the microstrip line for impedance matching. So you can design microstrip lines for impedance matching. So basically like that uh, uh, so so uh, so so if you use like the high impedance line and short length, basically you can realize the inductors and capacitor based on your length and width of your transmission of your microstrip lines. If you use high impedance line with short length, that will behave as inductor. And if you use low impedance line with with short length, then that will behave as capacitor. So basically you can add the this passive component at the input and output port of your active device, and that basically you can achieve for impedance matching. But ideally like in the ideal case, this passive device are lossless, you can consider, but in practical cases this all the active and like the passive components will have some resistance and some loss associated with that. So that basically you need to you need to you need to take account of that. So this was the importance of the impedance matching. Also, like you can very efficiently analyze the microwave, all the active microwave or even passive microwave component by using by using the signal flow graph and this Mason circles or Mason's rules. You can basically like you can model let's say this is your two port devices, which is S11, S12, S21, S22. So this is connected, let's say it's driving a load, which is ZL, and this is the input impedance is Z0, and here the like the here the input impedance is gamma, reflection is gamma. And basically there you can write in terms of voltage, you can write in terms of voltage, you can write as a this is the A1, which is the reflected wave, and this is the B1, which is transmitted wave. Similarly, A2, which is the reflected wave from the load, and this is the transmitted wave from the load. So this you can efficiently uh, represent by the this port. You can efficiently represent by the signal program. So each node you can correspond to each node in the signal flow graph, and like each direction you can basically represent by your the corresponding scattering each gain along the path you can basically represent by the scattering parameter based on that. So I think I lost my internet, so yeah, I'll just, I don't know what's. So yeah, so that is the gain along that path by the scattering parameter. So from A to B, so you can represent by S12, and that basically, and that you can, this you can represent S22, and this you can represent by S11, and this you can represent by S21 from port 2 to 1. And also you can represent this, here is the gamma L. So this is gamma L, and this is basically the your input ports are basically one gain, and also here the unity gain. So this is your A1, this is your B1, this is your B2, this is your this is your uh, this is your B2, this is your A2. So this is in between the A1 and B1, basically your gamma in has your A1 and B1. Basically, you have gamma, and you have so this is basically A2. This is basically B2. So now basically you need to calculate the V1 by the reflection coefficient. Basically you can, so with the Mason's rule, you can calculate the transmittance, basically transmittance along this port. You can calculate by the let's say two nodes. So if two nodes are connected by the different path, so let's say this then if that path has total gains length is, so basically you can define, so let's say G, this is H. So basically you can define the transmittance function as sum of path gain Pk delta k by delta. So this is you can so then basically you can define, so basically so the this pk is the this the path gain, path gain of kth path, and this delta k is the value of delta using loop not touching kth path, and the delta equals to 1 minus uh, sum of like 1 minus sum of all individual loop gains plus sum of sum of product of uh, this is the sum of product uh, of loop gains of all possible combination of two non-touching loops. Similarly, you can write the sum of product of loop gain of all possible combination of three non-touching loops. So similarly, you can write for others, and that basically that comes in the denominator. So to analyze with the signal flow graph, so we are going from here to here, this node to this node. How many paths are there? So let's mark the path. So one path is this one. So one path is this one. Other path, this, let's say this, call this as one, and the other path is this other path is correspond to this. So let's mark this as a 2. And what are the number of loops? So loops are those which you end up it's like if you start from a point, then if you end up at the same point without any, like, and you can't move against the arrow marks. So like if you move along the arrow marks, so basically how many number of loops you can make. So there's one loop. So let me mark with a different color. So the one loop you can make like this, and other loop you can make like this. So the other loop will be this one. So there are two loops in this. So the so then basically like the so so then basically you can write that delta. So P1, this path 1, so P1 you can write as a S11, and P2 you can define as, this is S12. This is so P2 you can define as S12 S12 multiplied by gamma L multiplied by S21, right? And then delta you can define as 1 minus sum of all so sum of all sum of loop gains of all two non-touching loops. So then basically the product of actually basically you can write this is one non-touching loop. So for P1 path, it is this is the non-touching loop. So you can write uh, you can write this as so basically you can define as delta 1. So this for this path, basically what are the non-touching loop gains. So then you can define as the S22 gamma L Similarly, for two paths, you can define as the loop. There is not even this like there are no non-touching loops are there. So basically, that you can write. And basically now you once you find the k, and even you can write the delta as 1 minus s22 delta gamma l. And basically now you can apply the Mason's rules, and basically now you can write as so that basically t21 you can calculate b2 by b1, and which is equals to uh, so that basically you can calculate like the even you can calculate both the you can calculate the uh, gamma in. So basically gamma in is basically equals to the a1, so this is b1 by a1, and which is equals to the uh, this path. So basically this is equals to p1 delta 1 plus p2 delta 2 divided by delta. So that basically you can see like that basically s11 plus s12 gamma l s21 minus 1 minus s21 gamma l. So this is your reflection, and the transmission coefficient you can write as B2 by A1, and which is equals to the your you can write as P1 delta 1 by delta. So that basically P1 is the this so the transmission coefficient you can write from this is B2 and this is A so no no so this is A1 and this is B2. So then basically you can write as S21. So basically the for B2 the gain is B2 the gain is so just no no this is A2, this is no no this is B2, and this is A2. So basically now you can write for that. So P1 is path 1 is P1 is so between this and this terminal you need to take. So P1 is S21, delta is 1 minus S22, gamma L, delta 1 is 1. So basically that you can write as so you can write as P1 delta 1. So S21 divided by 1 minus S22 uh, gamma n. So basically, in that way, you can get all the coefficient from the signal flow graph and the Mason's rules. You can calculate each of the parameters. So that basically like you can use for to analyze the network. So there are so that basically you can calculate different kinds of gains and those parameters with the Mason's rules, and you can analyze the microwave networks very efficiently with the Mason's rule. So that was the brief summary of the content I covered today. So I will be solving this problems related to the content covered for this week, and then later if I need to introduce some concept about the some which I missed, then I will briefly introduce, and then I will just explain there itself. So if you have any doubts, I will pause for some time, and if you have any doubt, then you ask, or otherwise we will move further. Okay, so let's move further. Uh, the uh, this first problem talks about the clockwise movement along the constant resistance circle into the upper half of the Smith chart. So basically, now you are basically, let me draw a Smith chart. So that, and this is the uh, gamma equals to one circle. So basically, now what is saying? Let me draw the constant resistance circle. So this will be the constant resistance. So this upper half, the clockwise movement. So if we draw the these constant susceptance or constant reactance circle. So basically, you are moving clockwise in the positive half. So let's say you are here, you are moving clockwise in this direction. So as you can see, like you are, so this is the positive reactance. So let's say this is, if this is j point 0.1, this is j point 0.2, this is j point 0.3. So basically, like you are adding, so you are basically adding the basically you are increasing the this, and basically you are increasing the j omega l. And if you fix the omega l, so basically this effect is same as adding the value of inductors. So uh, so that basically so that means you are increasing a inductors in the series or inductors. Then basically so the correct answer responding to this will be reduce the value of inductor, that is wrong. Increase the value of inductor, that is correct. And the capacitor value decrease, that is wrong. Because the capacitor, if you consider, then you need to move in the lower part actually. So that to correspond to capacitance. And the fourth option is also wrong. So the correct option is the first option. So let's move. If you have any doubt, I will pause for some time. Just see this question whether it's comfortable for you, and then otherwise we will move further. Okay, so let's just move to the next part. So this the so let's say we draw this circle, and then we draw the constant resistance circle. So let's say this is the point. We draw the constant resistance circle. So this is the divide line dividing the plus half. Now it is saying that constant movement. So let me draw the reactance circles also. So here it's, so this is like minus j point 1, this is minus j point 2, this is minus j point 3. So that's how this is increasing. Now, what will happen is, so the counterclockwise movement along the constant reactance resistance circle in the lower half of the Smith chart. So that basically now you are moving along this. So let's say if you are at this, then basically you are moving in this. So basically you are adding uh, a uh, a the capacitor value, and which value get increased. So if you are moving in this to this point, so basically you added a capacitance. So that minus j, let's say you add a 0.2, and 0.2 this will correspond to 1 by j times omega c. And if you fix the omega and j, you can take you can write as a minus j by omega c. So the c and omega both are positive. So basically you add the value of capacitance, and you increase basically the value of capacitance. So This basically, so let's say this reduce the value of inductors, that is wrong. Increase the value of inductor, that is also wrong, because inductor you should be in first half. And this is the capacitor value decrease, that is wrong, because the in as we have seen, the capacitor value is increasing, and the correct answer is fourth one, which is the capacitor value increase. So then let's just move to next problem. Which option is correct? So this problem is talks about the microstrip line, and which was discussed in the main class, and actually how you can model the inductance and capacitance with the microstrip line. So the series inductor can be modeled by the short length of high impedance microstrip line. So this is correct. Series inductor can be model length the short lengths of the low impedance line, that is wrong. Shunt capacitor can be modeled by the short lengths of high impedance, not high impedance. This should be low impedance. Uh, a shunt capacitor can be modeled by the short length of low impedance line. So this is also wrong, and this is also. So the correct option is the first one. So if you have any doubt in this, so please ask, and otherwise, if you don't have anyone, so we will move to next problem. Okay, so let's just move to next problem. Then for the uh, for the load impedance ZL equals to 50 plus this at 1 gigahertz, the value of reacting element required to match the 50 ohms are you need to ask. So basically, for the load impedance, and actually, we can calculate with the load impedance, we can calculate the uh, so basically we can calculate the normalized load impedance. So this is ZL is given as 50 plus J times 60, and if you divide by 50, so small ZL will be equals to 1 plus J times, so this will become J times 60 by 50, right? So this will be the J. So real part is 1, and the imaginary part is 1 point. So this you can write as 1 plus J times 1.2. So now if you draw the Smith chart, so let's just draw the Smith chart. So this is the circle, and basically the that basically you can draw this is the gamma this is the resistance equals to one circle. So this one is given, and because this is 1.2 positive, so you need to move the up in the direction. So basically, like that is so that is the this is, let's say it's the 1.2 point, and basically you can mark this point, and this is r corresponding to register normalized resistance equals to 1. So now basically now you need to match this load. So uh, so the value of reactive element required to match this load, basically you need to move this circuit. So basically you need to move along the negative direction in the clockwise. So basically if you add if you add the equivalent the shunt impedance equivalent to the in the parallel. So basically the if you move add the series shunt resistance, so basically that you can just move in the clockwise direction. So then basically you just need to add the capacitor to bring that back. So that inductance, that reactance should be equals to this. So the you need to write this. You need to add minus minus j times 1.2 to this. So this is equals to minus j times 1.2, which is equals to minus j by omega c. And this you can write as j will get cancelled. C equals to 1 by 1.2 omega, and this 1 by 1.2 into omega you can write as 1 gigahertz. So this that is this is 2 multiplied by 3.14 multiplied by 1 into 10 power 9. So that basically now you can divide by this. So this is around 2.4 times 3.14 times 10 power 9, and this will become 6. So this will become 7.5 something. So this will become 1 by 7.5 times 10 power 9, and this will become this will become so then basically this will become, if you put like those, so this 10 by 75 it will become, so this will become 3, and this is will become zero point 0.4, and this will become 0.12 something. So 0.313, and this will become 0.13 into 10 power 9. So then basically it become a nanofarad. I think it will become Z omega c. So we are not sure. So the correct answer, if you solve, did I make a mistake? Uh, so basically, like you need to add the capacitance, and the correct value will be will come around this 2.65 picofarad. I am not sure what I did wrong. Okay, so let me just try to revisit this problem maybe in the next class. So then basically, this again, so for load impedance, this will come down in the circle. So basically, this is if you calculate the normalized impedance, then this will become minus point j times 1.0 at 1 gigahertz. The value of the match the 50 ohm line. So basically you need to this you if you draw the Smith chart, and this is basically your uh, r equals to one circle. So then basically then you are in the negative side. So basically you are somewhat here. So you are somewhat here. So what you need to do, you need to add a positive j times 1.0 to move along the this. So the correct answer will be inductor, and basically inductor equals to j times omega L, and that j will get cancelled. So L will be equals to 1 upon 1.0 times omega, which is equals to 1 upon 1.0 into 2 into 3.14 multiplied by 10 power 9, 1 gigahertz. So this will become 6.28, 1 by 6.28 multiplied by 10 power minus 9, and this will become this will become zero point 0.1. So then 0.1 and 6 something, and this is 10 power 9. So basically, you need to, or it is given. So basically, the correct answer will be correct answer will be 7.95 nano. So nano Henry. So basically, this is minus. So this will become minus 7.9. It will become, yeah. So ideally, it should be coming 7.95 nano Henry. So then basically, like you need to add the like the in the series, you can add the inductor value basically to bring this at the at the at the center of the Smith chart. So with this, let's move to next problem. So so this so let's so then basically, like this problems is so this problem talks about the signal flow graph. This is V1, this is V2, this is V3, and your V3 is S32, and this is S21, and this is S21, this is S22, and we need to calculate V3 by V1. So basically, like from V3 to V1, the paths are there. So if we draw the paths, so basically the path will be this path. Only one path is there. So P1 is equals to S21 multiplied by S32, right? And then basically now let's just calculate delta, which is equals to 1 minus sum of the all the loop. Basically this is the loop, a non-touching loop we need to calculate. So 1 minus uh, all the non-touching loop which does not touch this path. So then basically like the sum of product of all non-touching loops. So that basically you can write this as basically so you can write this non-touching loop as 1 minus S22, because this not, and delta 1 you can write as the corresponding to this will be like the sum of the product of the loop which does not touch the first path, and that will be equals to 1 on. So then basically like so then it will become uh, then the like your V3 by V1 will be equals to P1 delta 1. So this will become P1 delta 1 divided by delta. So this will become S32 S21 divided by uh, multiply by 1, and this will be equals to 1 minus S22. So the correct answer will be S21 S32 1 minus S22. So the this option is wrong, this option is wrong, this option is wrong, the correct option is this one. So that basically you can use to drive the use for signal flow graph. So then basically you can calculate the so this is the so if you have any doubt you can ask, or otherwise I will move further. Okay, so let's move to further. So the S11 is so the condition for unstability is a transistor has the following S11 parameters. So basically, like this so if that basically like the you can write as the so that's right. Okay, so the following are the S11 parameters. So basically, so uh, so this uh, this basically like the condition of a transistor has the following parameters, which like all the parameters are given. So transistors is unconditionally stable means so we can calculate the gamma in basically like you can calculate the uh, stability criteria. So basically like that unconditional stability you need to drive. So that basically you can write in terms of scattering parameters, and that you can like you can just solve uh, by so that basically like you need to follow this input stability condition. So that is basically gamma out of gamma s equals to 1, which is equals to s22 plus s12 gamma s s21 divided by 1 minus s11 gamma s equals to 1. So that basically you can you can consider this corresponding to the region, different region. So basically it is the conditionally stable or conditionally unstable. You will find that the transistor corresponding to this is potentially unstable. The correct answer is this. So this instability like condition unconditionally stable criteria it does not meet. So basically that you can use for to analyze. So with that, let's move to next problem. This for unilateral devices, condition must be satisfied. The condition must be satisfied is basically like the back reflection should be zero. So like the S21 is basically from input to output port. So basically unilateral device, your back reflection should be zero. So your S12 will be equals to zero. So the correct assumption, this is from forward transmittance and this is the backward transmittance. So these other options are wrong. So the correct option is V1. So then basically this talks about for a device to be unconditionally stable, which condition must satisfy. C and R denote the center and radius of the stability circle. So this was discussed in the class that for unconditionally stable your uh, gamma in must be less than 1 and gamma out must be less than 1, and gamma in and gamma out you can write in terms of S11 and load parameters, and then basically you can write this as the criteria will be equals to gamma L minus CL less than RL, and output stability criteria you can write uh, gamma S uh, uh, gamma S R minus CS uh, must be greater than 1, greater than 1, greater than 1 for basically word for basically S22. So basically, so you need to put the S22 and S1 condition. So if your CL is less than, so S22 is less than 1 and S11 is less than 1. So the condition will be the third one. So the CL minus RL greater than 1 and the mod of CL minus RS, CS minus RS should be greater than 1. So the correct answer is third one. For detailed derivation, you just please go through the detailed derivation in the class. So that like the for the scattering parameters given in the problem 7, the value of load stability circle and the radius of the source stability circle R. So the load stability circle. The center of the load stability circle basically you can define as basically this the center you can define as uh, CL. Basically you can write as a S22 star minus delta star S11 divided by S22 minus delta square mod S22 square, and that basically this is your center of the circle, and the radius RL is given by center of the load and radius of the source stability circle. So RS is basically the RS is basically your RS time gamma S is equals to mod of S12 S21 divided by mod of S11 square minus delta square. So that is your RS. So basically like yeah, this is your radius of your that circle, and if you calculate by putting all the value of plug in all the value of your S11 S12, you will find that the correct answer is third one. So basically like the this have been written in the polar coordinate form, so you should be very easy to easy to approximate in terms of the polar coordinate form. So basically this was the problem solving session for this today's class. I will pause for some time. If you have any doubt, please ask, or if you don't have any doubt, then we can end this session and we'll meet next week same time in the same slot. Okay, so if there is no further doubt, let's just end this session here today. So we will meet next time in the same slot, same times, and we will have like one extra session for clearing doubt this Sunday. So please try to attend that session, and it will we will get through all the concept related, all the doubt session related to the content which has been presented up to now, or which is maybe relevant for the midsem or other sort of exams. So please attend that session, and we will meet maybe on Sunday this week. So till then, thank you so much for listening this session, and I wish you great uh, I wish you great success in this course. So bye bye, good night, have a nice time, great learning. Thank you so much.